Well, AP Physics 2, we find ourselves once again at the start of a new unit, specifically Unit 3 on electrostatics. Now, up to this point, the two units we've covered so far, so that's fluid mechanics and thermodynamics, have been kind of in their own little separate boxes. They're kind of two really individualized units that aren't going to connect overly much to the rest of the year, but starting from this unit onward, all of the units are really gonna build. So let's go ahead and look into what exactly electrostatics is and get a brief introduction to the topic. Now, we actually started talking about electrostatics last year when we discussed electric charge and the electric force, so today should largely be a review. It's going to be mostly stuff we've already covered, but it's been a while, so I think it would be good to hammer out the details once again. So what exactly is electrostatics, and what does that term mean? Well, we've known, and by we I mean humanity, has known about electric phenomena for thousands of years, and it was documented that in at least 600 BC, it probably was known way before this, that if you took a piece of amber, which is essentially this yellow stone here, which is basically fossilized tree sap. If you've seen Jurassic Park, it's what the mosquitoes are trapped in. You could get this amber that if it was rubbed on clothing or on fur, it could have easily been like a piece of jewelry, for instance, that it would attract things to it. And when I mean things, I mean like little tiny pieces of lint or maybe little tiny twigs. Or it was noticed that it would attract these things to its surface. And so, it was kind of assumed that this had something to do with probably magnetism. They knew about magnets at least a few hundred years later, and so it was assumed, okay, this is probably the same thing. Now, because of that, that was the prevailing view for about 2,000 years, until about the 1600s, when a scientist by the name of William Gilbert, he was English, basically experimentally investigated and determined, no, this is a separate phenomena from magnetism. They're two different things. We now know that they're related, but they're two different things. And he coined this term electricity because of the fact that the ancient Greek word for amber is electron, and essentially was saying that it was like this phenomena you would see with amber. And additionally, going with statics, this is no different than, for instance, when we did hydrostatic equilibrium, we were looking at fluids when they were at rest, not when they were flowing. Same sort of idea here. Then when we're looking at electrostatics, we're looking at electrostatic equilibrium, which means that we have some sort of system of charges, and they're all going to be at rest relative to each other, at least at the instant of time that we're analyzing. Now, a couple things here. This is where we get the term static electricity from, so I know you're all familiar with that when you get like a shock or something. That's basically where this term comes from. But that means we're only considering them at rest, but that's not super realistic, right? Charges are going to be attracting and repelling each other all the time, but we are only looking at the instances when they're at rest, and then we could look at a different instance when they're at rest. So we're not going to look at any sort of flow. In other words, no current, no electric current. So first, let's talk about what pieces of matter possess that allow them to experience these electric forces, and that is electric charge, often just called charge, which we abbreviate with a capital Q or a lowercase q. Both are totally acceptable. And this is a fundamental property that matter may possess, not all matter has it, but the matter may possess, that causes it to experience an electric force from another piece of charged matter. In other words, another piece of matter that also has a charge. Now, we know that there's a few different ways this can be seen, and this has been historically known for at least a few hundred years, that there were multiple types of charge. Specifically, there appeared to be two, because sometimes these charged objects would attract each other, and sometimes they would repel each other. And so these two types of charges were labeled as positive and negative. Now, that was done by Benjamin Franklin in 1747. It is totally an arbitrary term. He could have flipped the positive and negative. In fact, many people would have preferred that he had done that. And what we know specifically is that if they are unlike, that these unlike charges will attract. So if you have a positively charged object and a negatively charged object, they attract. But if they are like, if they are either both positive or both negative, they will repel. Okay, now additionally, the unit of charge is the Coulomb, which we abbreviate with a capital C. Now, you may remember this, that a Coulomb is a humongous amount of charge. In fact, it is 6.25 times 10 to the 18 electrons. That E actually stands for the elementary charge. We'll get there in a second, but essentially, you have to have, trillions upon trillions of electrons to have a single Coulomb. Now, because of that, we often deal with much smaller metric units. So you might see, for instance, little mc, this is mu c, nc, and pc. And what those stand for is millicoulomb, microcoulomb, nanocoulomb, and picocoulomb. And it's pretty good to familiarize ourselves with that milli is times 10 to the minus 3, micro is times 10 to the minus 6, nano times 10 to the minus 9, pico times 10 to the minus 12. We're going to see all those pretty often. But as we just said a second ago, 1 Coulomb possesses 6.25 times 10 to the 18 elementary charges. But what is this elementary charge, which we abbreviate with just a lowercase e? Well, all charge is quantized into units of the elementary charge. So what does this term quantized mean? Imagine you have Legos, for instance. And if I have Legos, they come in a variety of sizes and pieces. But ultimately, like if I look at this block here, it seems to be really made of 4 of this one piece block. So let's go ahead and say that this is my quanta of Lego. So in other words, all of these blocks come in integer multiples of that quanta. I could have, this would be 1 quanta of Lego. This one here would be 1, 2 quanta of Lego. This would be 1, 2, 3, 4. This would be 1, 2. I can combine them, so I might have like 4 and 2, so this would be 6. But I can't have, for instance, a half. If I have this as my quanta, that means that this is the indivisible piece. I can't get to anything that is any smaller than that. So I can't have a fraction. I can't have a decimal. So because of that, we have all charge comes in these integer multiples of the elementary charge. I could have 1e, 2e, 3e, 4e, etc. But you're never going to have 1/2 e or 2.7 e. Now, the smallest isolated positive charge is the charge of a proton, which is plus e, and the smallest negative charge is the charge of an electron, which is minus e. E is just the number, plus and minus is the sign. And 1e is specifically 1.6 times 10 to the negative 19 coulombs. So if I have 1e, that would be 1.6 times 10 to the negative 19 coulombs. 2e would be that times 2, so 3.2 times 10 to the negative 19 coulombs. So I can have those, but I can't have 3. Can't have 2.5. I can only go from 1.6 to 3.2 to the next one, which would be 4.8 times 10 to the negative 19 coulombs, etc. So that would be the charge of a proton and the charge of an electron, but they would be positive and negative, respectively. Additionally, last year, and honestly way back in chemistry, you learned about Coulomb's law, which Coulomb's law is how we quantify the electric force for point charges. Now, what exactly do we mean by a point charge? We mean that if we're using Coulomb's law, we're only using it with very, very simple charge arrangements. So these point charges should be essentially little spherical pieces of charge. So I might have some charge Q1, some charge Q2. They're separated by some distance r. It doesn't matter if these are positive or negative when I do the calculation. So I get this equation here, Fe, the electric force in newtons, is equal to K times the absolute value of Q1 times Q2 all over r squared, where Q1 and Q2, so those are the charges of each respective point charge in Coulomb. So if it's positive or negative, you can stick those in. You just have to remember to take the absolute value, so we always end up with a positive number. K is Coulomb's constant, we'll get there in a second, and r squared, so r is the separation distance between the two centers of these point charges in meters. Now remember, r is not a radius, it is the total distance between the two. Now, a few things we need to notice here. One, that the force, the electric force, is proportional to the size of the charges. You have bigger charges, a bigger electric force is generated. Pretty straightforward. Additionally, it is inversely proportional to the square of the separation distance. So this is something we call an inverse square law, meaning that it's very, very strong nearby, but as soon as they separate out, it dips down very, very quickly. Additionally, we have Coulomb's constant, which is this lowercase k here, and Coulomb's constant is 9 times 10 to the 9th newtons times meter squared per Coulomb squared. Remember, all that is a proportionality constant. It just basically gets us from Coulomb squared and meter squared 2 newtons. It's just getting our numbers to be consistent. That's all that's doing. Lastly, a couple things to note. One, this just tells us the magnitude of the force, so how many newtons it is, 1 newton, 2 newtons, whatever. If we want to know the direction of the force, we need to look at the charge types. So for instance, if this one was positive and this one is negative, the force on this charge would be to the right towards the negative charge, and the negative charge would be to the left towards the positive charge. They would both have the same force because it's like a Newton's third law of force pair. Whatever one charge applies to the other in electric force, the other charge applies an electric force right back. Now, if they were like charges, so if they were both positive or both negative, they would instead repel each other. Okay, lastly, these forces are vectors, so they should be combined properly. So for this, pretty straightforward. But let's say we had multiple charges. Well, then we need to look at each respective electric force and then combine those together properly using vector addition. So let's look at a brief practice problem to conclude our lesson for today. So we have here a system of 3 charges. We have a big charge on the left, which is positive 6 microcoulombs. That should be annotated as Q1. There we go. We have a charge on the right, which is negative 4 microcoulombs. And then we have a proton located exactly between the two, and it's separated by both of them by a distance of 20 centimeters. So we want to determine the acceleration of the proton at this moment in time. So in other words, if we put these, like imagine Q1 and Q2 are stuck there, you put the proton right there and you release it. What would its initial acceleration be? All right, now I want you to go ahead and see if you can try this on your own. This should not be anything too terribly new, so pause the video, give it a shot, come back, let's talk through it. Okay, well hopefully you gave it an attempt. But first thing we need to do is we need to figure out, okay, what is the electric force on the proton from each of these 2 respective charges? So first, I'm going to do the electric force, so electric force 1 from the big positive charge in the proton. So I just stick this into Coulomb's law. KQ1, the Q of the proton, over R1 squared. So Coulomb's constant, 9 times 10 to the 9th, newtons times meters squared per Coulomb squared. The big Q is 6 times 10. Okay, so remember micro is negative 6, so 6 times 10 to the negative 6 coulombs. These protons charges out the elementary charge, that would be 1.6 times 10 to the negative 19 coulombs, all over 20 centimeters needs to be converted to meters, so 0.2 meters squared. Remember this square, this is where I always see people make mistakes, they forget to square the R. We take our calculator, plug that in, we get 2.16 times 10 to the negative 13 newtons, and we know that the proton is going to accelerate to the right from this force because they are both positive, so they are like charges, they're going to repel, so the proton is going to go away from it. And now I do the exact same thing with Q2 in the proton. I just take the red negative 4 microcoulomb charge, and I take the proton and I stick it into Coulomb's law again. And when I do that, we're going to get 1.44 times 10 to the negative 13 newtons, also to the right, because these are unlike charges, they're going to attract. So the proton is going to be attracted to Q2 and repelled from Q1. So I have these 2 respective electric forces. So if I want to know the net force, I need to combine them using vector addition. So tail to tip vectors. Now, in this particular situation, it's real easy because they're both pointed to the right. So I just add them together. It gets more complicated if we start doing like 2-dimensional arrangements of these particles. So I basically add these together to get the net force will be 3.6 times 10 to the negative 13 newtons to the right. And if I want to know the acceleration of the proton, well, I can think back, okay, Newton's second law tells me that acceleration is equal to the net force over the mass. Well, how do I get the mass of the proton? Luckily for you, it's on your equation sheet. So go grab your equation sheet, look at the constants, and so we plug that in. The net force was 3.6 times 10 to the negative 13 newtons to the right. The mass of the proton was 1.67 times 10 to the negative 27 kilograms. We divide, and we get a humongous acceleration of 2.16 times 10 to the 14th meters per second squared to the right. Now, that seems like a humongous number, but keep in mind a proton is incredibly tiny. So even though this force was quite small, the mass was even smaller. So that concludes our first lesson in this unit on electrostatics, just basically reviewing over some concepts from electric charge and electric forces. So really, can you evaluate the accuracy of scenarios by utilizing the quantized nature of charge? In other words, if you're given a scenario, can you look at it and go, oh, okay, these charges are in multiples of the elementary charge, it all checks out, or can you look at it and go, wait, this doesn't make any sense, these can't be multiples of the elementary charge. Additionally, can we accurately predict the electric forces present between a system of charges by, one, making sure that if they're unlike, they should attract, and if they're like, they should repel, but also just taking into account Coulomb's law. So far, we've only looked at a one-dimensional example, but you're going to start practicing two-dimensional examples pretty much immediately.